That's okay. Cool. All right. Would you like the lights dimmed a little bit, or?
Whatever people.
Dim a little bit. Okay.
Just a second.
Oh yeah. There we go. Great. So we're very happy to have Matt Buckley from Rutgers here, who's going to talk about using Gaia data and machine learning to infer some cool properties about dark matter and the Milky Way. So without further ado, go ahead now.
Thanks for the invite. It's been a surprisingly long time since I've been here. I went to the wrong building.
Oh, if you want this.
Okay, so I wanted to talk about a couple of things that myself and a whole bunch of collaborators at Rutgers and elsewhere have been working on over the last couple of years using astrophysical data to try to infer some properties of dark matter, and we're using a bunch of ML techniques, which I'll try to explain as I go through. We are not just asking ChatGPT what dark matter is. I want to make that clear. There is I hopefully convince you there is a responsible way to do machine learning and physics. So just a little bit of motivation, because I am a theorist, particle theorist, at least originally. I apparently have ended up as an astronomer, and I'm not really sure how that happened. Oh, I do know the answer. If you ask a bunch of astronomers about dark matter, eventually everyone thinks you're an astronomer. So, you know, as a theorist, right, like there is a theoretical motivation for why I think we need to be spending a lot of time thinking about, you know, what astrophysical data is telling us. And that's because we have this motivation, right? We know dark matter exists. And the only ways we know that are from gravity, right? And specifically gravity is applied to astrophysical systems, right? So you have lensing, right? You have rotation curves, you have, you know, the detailed properties of the early universe. All of that points you in the same direction, that there is some new physics that you don't understand that is giving you dark matter. And then as a particle physicist, what you do is you sit down, you cook up a whole bunch of very cool and very good ideas about what dark matter must clearly be, and you go and you look for it in various experiments, right? You can do, this is, you know, collider physics constraints on some particular models of dark matter. You can look for it in indirect detection, you know, axion models, direct detection, all of these things, right? So you can look in all these different places, and over the years, I've worked on many of these different ideas. And unfortunately, right now, other than some like maybe weird hints that you can go argue about for a very long time, right? It's like some gamma ray excess from the galactic center, right? There is no clear signal of a particle physics explanation for dark matter, right? Which doesn't mean there isn't going to be one, we just don't want to have one right now. So you have these negative results, and as a theorist, I don't want to just sit around and wait, you know, for somebody to finally give me a positive result. So I need to go out and think about what other data is out there that might point me in the right direction. And if you go back and just start thinking, well, how did I know what the problem was to begin with, and where, you know, how did I have an idea of where I should look? Right? It was all coming from gravity. It was all coming from these astrophysical systems. So if you think about dark matter in the universe, right? And here is the simulation of a galaxy cluster. And then you have, you know, a spiral galaxy would be living in here, and you're seeing the dark matter. You see, oh, there's all this like substructure down, right? That's a prediction from the early universe, and a prediction in this case, you know, of just a particular kind of dark matter, one that doesn't have any kind of interesting interactions, at least down to a certain scale. And then if you start adding particle physics to that, you can change what happens at these small scales, right? So this is an old paper of mine where we added in some self-interacting models, and looking at the power spectrum, this would sort of be the answer you should get with cold dark matter. And starting adding in different models of particle physics, you can start getting interesting kind of ripples and structures in small scale structure, which you could then hope to see if you were lucky enough to be able to see dark matter in the universe. And then if you have non-trivial interactions, you know, this can show up in changing the inner slopes of, you know, small structures of dark matter, like dwarf galaxies and things like that. So these ideas have been sort of kicking around with Annika Peter. In 2017, we wrote a kind of very long review article thinking about all of the ways that astrophysics could try to get at dark matter particle theory that changed what dark matter was doing on a particular scale. Right, so what this is, you know, here you have the scale at which a gravitationally bound object of dark matter will change from sort of the canonical gravity-only version of dark matter, right? You start adding in some non-trivial physics, and maybe you can change something around the scale of a galaxy or a dwarf galaxy, get down to very small scales, right? There aren't any stars we expect in such objects. So now you have a problem. How do you find something of 10 to the 5, 10 to the 6 solar masses? WIMPs predict that there should be structure kind of way up here at 10 to the minus 6 solar masses even, and you can see those, if you knew they were there, you now have some pretty solid evidence about certain models being true and others not. And then here was just sort of all of our ideas and sort of surveys of the literature of what people had suggested are ways that using astrophysical searches you might be able to get at structure at those particular scales. And that really helped me kind of focus my thinking about maybe what I should be thinking about next. And what I'm going to be talking to you about is largely things that are using stellar kinematics, so how stars are moving within a galaxy to try to get at, in the end, the structure of objects between 10 to the 8 and let's say 10 to the 12 solar masses, and then eventually, we hope, be able to connect that to particle physics, right, which models. And today I'm mostly kind of talking about, we have these observations, what can we do with them to try to learn something about the dark matter structure. So that's sort of where I'm coming from as a theorist, and it's a really interesting time right now because astrophysics has just a tremendous amount of data. Right? It's an era of big data in astrophysics, right? So you got Vera Rubin, LSST coming on. You'll see the entire southern part of the sky. There are existing surveys that cover large parts of the northern sky. And the one that I'm most interested for the purposes of this talk is Gaia, right? So Gaia is a space telescope. Here's a nice little artist rendition of it, right? And what it's doing is it's looking at stars in the sky repeatedly with very, very high accuracy for their location, and it's accurate enough that you not just get their position and their parallax, which gives you their distance, it also gives you their proper motion on the sky. So you can actually see the stars as they drift across the plane of the sky, not just getting the radial motion, right? So you have now, at least in principle, full 60 kinematics for a very large population of stars around the Earth. Right? So if you look at the numbers, Gaia measures about 1.5 billion stars in the galaxy. If you actually downloaded this picture in high resolution, it's not like, it wouldn't be just pixels filled with like bright and dark parts, it would be individual dots, right? This is the picture of the galaxy as seen by Gaia, where every bright spot should be a star, and if you try to download it at full resolution, it will take a while, right? So it gets you parallax, it gives you photometry, so you get color and magnitude. You do get spectroscopy. It is a bit limited because it's trying to look at a lot of stars, not looking with very, very high spectroscopy at a limited number. So you get proper motions for, at least in principle, for all these stars, though many of them, the proper motion you'll get will be 0, because you just can't see it, it's too far away. You get line of sight motions from the spectroscopy for about 34 million stars in the DR3. That will go up to 150 million by the end of the mission. And I'm interested in this data set as a set of data in 4 dimensions. In that case, it would be like position on the sky and proper motion on the sky. 5 dimensions if you have parallax, or 6 dimensions if you have the full 6D position and velocity structure of those stars. So I'm mostly interested in 6D for the ones that give you the line of sight. Right, so now you have like just a map of stars around you as they move through the galaxy. And what can you do with that? Well, right now, there's a lot of talk of machine learning, right? And I think there's certainly things you can do with machine learning that I don't think are terribly useful, but there are some really, really useful and powerful algorithms that you can get from machine learning that I think are really, really useful for physics and for astronomy. And really what it's doing is just giving you new handles to try to look at very high dimensional data and very large data sets. A lot of what I'm going to be talking about today uses what are called normalizing flows. There's a nice review article here. What a normalizing flow is doing is it's learning a transformation between random data in some what we call latent space. So in this case, it's starting from a Gaussian, a 2-dimensional Gaussian, that's the initial like blob. And it's learning how to take that random initial data and map it to a final set of data that has a structure. So the end structure here is the 2 half moons tied together. And it's just learning like what function do you take to just go from that random data to that final data. And what that allows you to do is learn the probability distribution of that final data, right? You get the phase space density of your final data set. And basically what you're actually doing is minimizing the entropy. So that's actually, as a physicist, when I realized that, I was like, oh, that's kind of cool, right? You're learning how to measure the phase space density of that final data set by minimizing the entropy of the data. So this is just a very general technique. It's a thing you can do. You can do it in very high dimensional data, right? I'm going to be applying it to 6-dimensional data, and that's considered extremely low dimension for what normalizing flows are designed to do. So we had this tool, and we realized there was an application of it that we could consider. Right? So if I want to take this kind of set of stars around me where I have their position and velocity, one thing you can do is say, well, these are moving in a gravitational potential, which includes the dark matter. So this is what I want, right? And it obeys the Boltzmann equation, right? It's a gas of stars moving in a potential. And so, you take the derivatives of that phase space density and you have the Boltzmann equation, right? The problem with taking this and applying it to the data is that it's really hard to know what the phase space density of 6-dimensional data is, right? Like you have a bunch of data points and you want this function, f, and then you need to learn f well enough that you can take derivatives and have those derivatives be under control, right? And that's very, very difficult to do typically. The kind of key connection here is it just turns out that normalizing flows do a much better job for a given data set of learning f and its derivatives consistent with the data than non-machine learning techniques, right? I'm not saying that you have the true underlying phase space density of a set of data. But what I'm saying is that you get a better estimate of it than you think you would have any right to do if you had been just using non-machine learning techniques.
How do you measure it better?
You get practically in this case, I can show you that we do a better job in simulation, but you can also just get a closer estimate to if you know the true phase space density because you've generated fake data, you can get close to the entropy.
But is the ultimate question going to be like whether or not we match that, or whether we match like some particular observable, which might only depend on this, that, or the other?
Well, the problem is that it depends on the derivatives. So you can be really close, and typically what you'll see, we're very close to f, right? But then now you worry about the derivatives of f, and then if I actually want the density, not the potential, I need the second derivative. So errors start piling up, right? But what I can show you actually.
Before you go on,
Yeah.
what is a non-machine learning way of fitting a distribution?
So we're going to compare to like genes analysis and made to measure potentials. So for this particular case, the way that it has been done, and obviously there's a huge literature for this, we are, just applying a new technique to try to get at something from the Boltzmann equation. The way you typically do this is you say, well, I'm not going to get all of the derivatives of f, because f is going to be so sparse in this high dimensional data. So what I'll do is I'll kind of integrate the Boltzmann equation and take moments of it, and I'll get the genes equation. So now you just have number density, right? And then like averages of the velocities. And here's one example where you take data, very similar to what we're looking at. So here we are in the galaxy. That's where the sun is. This is off of the disk, right? This is towards the galactic center. Towards the galactic center, I believe, off of the galactic center, away from the galactic center. And you kind of have to just bin data in these big kind of cubes to get, derivatives of the average velocity within that. Or you can do made to measure or like fitting functions to the data to try to fully fit the Boltzmann equation using the functional forms that you have picked. What we're saying is that we don't have to guess the functional form that we're fitting to the data. We're allowing the data to tell us what that function is in a very, very general way that we don't have to specify. And I will show as I go through in this case, and I'm sure there's going to be data sets where this maybe is not the case. I can't say for sure in every context. But in this case, for a set amount of data, we can control these derivatives and get this function to get an answer that is closer to the ground truth than made to measure the genes analysis approaches for a set amount of data.
When you say made to measure, this wasn't a terminology that I was familiar with.
I am not an expert in this technique. I believe it is sort of picking a functional form for, for the derivatives that you need to fit and trying to,
And fit the parameters of that.
yeah, fit the parameters of that. So,
Often there's like this is usually in the context of extragalactic, right? So often it's a multi-Gaussian, it's a mixture of Gaussians model.
Yeah. There are examples within the galaxy for the gene simulation.
Yeah.
Right.
Okay.
So, and I'm not saying that those are like the wrong approach or, this is the only way to go. I'm just saying, at least in the cases that we were comparing with, when we took our technique, applied it to a set amount of data, and then took what we hoped was a fair representation of another technique and applied it to the same data, we got closer to the right answer without making symmetry assumptions. Because in many cases, you are assuming something about the symmetry of the data, right? That maybe north and south are the same, right? Or that there's no spherical, that angular dependence goes away so that you can bin data in some way.
Yeah, I was curious because one of the results from Gaia was also that the galaxy is not in equilibrium.
Yes,
So
I will talk about the lack of equilibrium. So let me go on a little bit, and then if it.
Cool. So just to finish my question, so I was curious, once you then compare techniques, what type of simulations you are comparing it
Yes. So testing with simulations, right? So okay, let me just back up. So this had been suggested by this paper, and then these two papers here. This paper used just a sort of galaxy that was just a sphere of stars, right? And this showed that you can recover that sphere, right? And this one used a more realistic galaxy, but it was still drawn straight from there wasn't any dynamics. It was just, this is the potential, let me pull stars from that potential and then fit to that. And then you have this question of well, you have a real galaxy is disequilibrium, it has all these observational effects. So we wanted to show that this technique could survive those observational effects. So we took a galaxy from the N-body shop, H277. This is what the galaxy looks like from above. We dropped a kind of fake sun right there. This circle is 4 kiloparsecs. That's what we're going to take as the observational range of Gaia that we can see. I'll return to that when I get to the real data. This is what it looks like in gas. So there is structure, there is disequilibrium. This is a real galaxy in the sense that it evolved from mergers and things like that, right? One thing to note is that we have to take star particles from this simulation. Those are the things that are in equilibrium. We then generate a fake star from that star particle, but only one per star particle. And there are only 154,000 stars within this sphere, which is a tiny number for this problem. Usually when you're trying to do a genes analysis, you would not use this few stars, and we actually ran into a lot of trouble trying to match the genes analysis onto this, because they don't really work that well with that few stars. So this is just showing you that we use masked autoregressive flows to fit the phase space density. So what this is just histograms of the original data is a black line there. And then we put in these normalizing flows to fit the data. And I'm just giving you a histogram. And the point is that the histogram and the real data all match up, right? We are fitting F pretty well without knowing what it was, right? We just gave it the data and asked it for a function in 6 dimensions that would match that data. And this is just the coordinate system. I'll come to these lines in a minute. Then we have to use the physics. We have to plug it into the Boltzmann equation. So what we do is what you usually do within the Boltzmann equation or genes analysis and say, let's assume that the galaxy is in equilibrium, which is to say that df dt is 0. So we minimize this combination, which is df dt, to numerically find this acceleration, right? The derivative of the potential gives you the acceleration. That's what we want, right? So we find an acceleration by minimizing this combination of the derivatives of the phase space density. That doesn't require it to be exactly 0, but it will try to at least get it close to equilibrium. And we'll return to whether that assumption is true later. And then these are our accelerations then. So x is sort of the direction towards the galactic center. Y is along the disk, Z is off of the disk. And what I'm showing here are the true values, because we have simulation ground truth, which is black, which you can't see, and then the original without errors, with errors, and then this would be the genes analysis. We just use it as the standard genes analysis adapted to this few number of particles to try to sort of show apples to apples, how do we compare? Right? And they look pretty similar. You can see some things kind of wiggle off in your directions. The genes analysis kind of loses the plot a little bit over here.
Sorry, this is just along some line in X? Is that what this means?
So this one would just be at z equals 0, y equals 0 in X. I can
It's like the
evaluate.
skewers.
Yeah, I can evaluate it anywhere. It's just
Yeah,
you
you
gotta
you
make
have
a
to be
plot.
able to visualize it.
Yeah, we tried to make 3D plots and they're not readable, unfortunately. So that gives you the accelerations. What I'm interested in is the dark matter. So I want the derivative of the acceleration to get the density using Boltzmann equation. So you can then, because you have this function.
Oh, sorry.
Yeah.
The phi, like you say you fit it, so it's what's the space of that phi lives in?
So in this case, all we are doing is we're saying, tell me what the vector is at this point at a given x that minimizes this. And the way that this works is, because I have a function f, which is dependent on x and v, this only depends on x. I can then sample from that function. I can generate basically fake stars at a given x at different v. And I generate 10,000 such fake stars at different velocities and run this sum over all of them. Because they all should be feeling the same acceleration.
No, but but you're fitting like what is the form of phi?
Oh, no, in this case, you should just read this as A.
Okay, then what is the form of A?
It is what, at any x, it is whatever minimizes
So
this
there's a
sum.
grid in X, Y, and Z.
So
And there's an A at each grid point? Or what is,
yes,
okay.
yeah. So this could be evaluated at any point where I have data. Right?
Okay.
It's just
you
I
can decide what
evaluated
you
it,
want.
in this case,
You
I
can do it
evaluated.
where you want.
Yeah.
Yeah, okay.
In this point, I evaluated it on 3 lines
Okay.
because eventually it gets very expensive to do, but you can evaluate this wherever you want.
Okay.
Yeah, and this is just whatever you get to minimize this function.
Yeah. Wait, is that guaranteed to be a gradient of anything?
No, so
Okay.
I will say we are correcting that problem right now.
Okay.
I just don't have the results to show you. I have the results. It works very nicely.
Okay.
But for this a pass, we didn't do that.
Okay.
Our first effort to do that failed, and we did this, and then we figured out what went wrong. So talk to me relatively soon and get those results. So then you take another derivative. So here we have to kind of, using this approach, because we don't have a function for phi or the gradient of phi, we do basically numerical derivatives over like a little ball. So any x you want, you pick a little ball around it and calculate the gradients of A across that, right? And so what you can see is that here is the true values, and then red and blue kind of overlap. That's using our machine learning techniques, and then you see the genes analysis starts falling apart, right? This is the disk, so we're at z of 0, and then you get an increase in the density, and then you can see the genes analysis is not that off, but given the sparsity of data, it does start drifting off. A real genes analysis on real data would do better. It's just that we only have 150,000 stars, right? Which is really too few for that. But it's the same 150,000 stars that the flow got, and the flow kind of gets closer to what, in this case at any rate, is the truth. So that seemed to work for the simulation. So the obvious thing to do is to take the real data. And it's kind of funny, the real data avoids the problem that we were having before of too few data points. Now we have nearly 30 million, right? So we take all of this, 29, 30 million stars within 10 kiloparsecs of the sun. Those are the stars that have the full 6D. So that's position, angles on the sky, parallax, so that gives you distance, proper motion, and what Gaia calls RVS, that's the radial velocity. We throw out the poorly measured stars. We are going to retain the full covariance matrix that Gaia provides us, so we can actually kind of perturb within errors to do error propagation. We're mostly going to be interested in the 4 kiloparsec sphere centered on the sun, and there are about 25 million stars within that. After about 4 kiloparsecs in this data set, the errors start growing too much, and we just kind of become insensitive to what's going on. So this is what the data looks like. We live here, and immediately you can see you have a problem because this thinks there's a lot of stars near us and fewer everywhere else, right? Which is not actually what is going on. It's just that Gaia sees stars, and if the star is bright but far away, it may not be seen. So this is color and magnitude for all of these stars. The Gaia spectrometer claims to be complete, so they can see every star that has an observed magnitude greater than 14, right? So anything here and below, if you put a magnitude 14 star as seen here at the edge of this, right, that will give you an intrinsic magnitude, right? The problem is that a star which is intrinsically dimmer but here will be seen by Gaia, but if the star was moved out here, it wouldn't be seen. So we kind of have this selection function. So what we do is we throw out stars that are close and bright if they're not bright enough that they would be seen at the edge of our observation window. So this is the intrinsic magnitude. We throw out all stars that are dimmer, right? There is a part of, I think this is the red branch. You see there's smearing. That's because we didn't color correct. We tried to, it didn't work. It's not complete across the sky, but that's something we'd like to deal with. So making that cut, you can see now you don't believe that there's a huge number of stars living where you are, right? Because you remove that observational bias. So this is face down. This is looking from the side off of the disk. But you can see there's still a low density of stars right here. That's because there's a huge amount of gas and dust towards the galactic center, and that's obscuring the stars. Right. So that's going to be a really big problem for us. If you look, you should still be able to see dust lanes, right? There are like wedges here. Those are all within the disk. So just prove that. Let me block off the disk. So I make this cut, and then you see, oh, there's more stars towards the galactic center. That's nice. That's what I'd expect, right? So I'm going to take the stars before the cut, but I'm going to recognize that within the limitations of my data, right now we have a problem directly in the disk because there is so much dust. This is the normalizing flow step through from sort of your initial latent space to the data space, and at the end of the day, you get something that looks like the data. So now you have F. You have F of X and V. You can take derivatives of it. You can propagate your errors through it. This becomes kind of expensive because you basically, the only way to propagate the errors through is just to retrain from the beginning. But we include all of the measurement errors. We include what's called a bootstrap that will get at the errors that you have because you have limited statistics, right? And then we include retraining error because you initialize your network differently every time, and that could introduce noise. So we are trying to propagate all of the sources of error through as well we can.
So I would have thought that error would lead to some sort of like, it's not just that your normalizing flow has like ripples in it, it's that the error smooths things, but that's not what you're talking about.
No, that, because we have no way to correct for that. Right. We do include that by reperturbing the data with that within its error ellipse. We take the entire data set and basically shake it by its errors and run the entire analysis through. And under the limit of small errors, that gives you a sense of how big your error should be. I will say it's not symmetric, and I'm happy to talk about it afterwards. We have thoughts about how to deal with that particular systematic error. But right now, we're just including it as a statistical error. So it kind of, I think the magnitude is correct, but the direction of the error is not necessarily.
But I mean, if your velocity errors were large,
and they are, yeah.
Then that blurs out the velocities. Yes. It leads to larger.
It's not, yeah.
Like it leads to a larger potential. There's a bias associated.
Yeah,
with
it leads to like smaller derivatives.
Yeah.
Yeah. So we try to get at the size of that bias, but I can't. Like there really should be a way to learn which way it should go. I'm happy to talk about that after offline. Right. Then there's this dust. So this is Gaia our Gaia data with, just plotting all of the stars. And then I'm over plotting it with a dust map. Don't ask me which one. I have it written down somewhere. I don't remember. There's like astronomers in the room, and I'm really worried. I brought up dust. Magnetic fields will not enter. Right, so you can see the dust map. If you look beneath it, there's like holes in the data, and that's just because we don't have stars there because there's so much dust. Well, at least the normalizing flow learned all of those holes, right? But what this means is that you shouldn't believe my answer anywhere close to the disk, right? Along the line of the disk, our flows are accurate to the data, but missing all of the stars that are truly there because it's just too obscure. But then you can go through, calculate the acceleration, minimize the disequilibrium. So this is again assuming that the system is in equilibrium. So this is our answer for the acceleration vector at the solar location. I'm showing you the solar location because Gaia has a measurement using quasars, right? So you have these distant quasars which should be, not accelerating, and so that gives you a fixed frame, and you can calculate our acceleration relative to that. And we are consistent within errors with their answer. So that's at least an interesting thing and a non-trivial one. If there was a lot of disequilibrium, you might expect these to disappear. These are just the acceleration, as you were asking, like, where do I evaluate it? Well, I can do this anywhere, so it's just kind of fun to make a grid of all the accelerations. And again, don't believe the answer in here because this is the plane. And so you have huge errors there. I think we're still okay close to the Earth because there's just not that much dust along that line of sight until you get too far away. So those are the accelerations now along different lines. So we did a line kind of through the Earth off of the disk, right? That's this green one here. Then we did lines above the dust in towards the center and above the dust kind of along phi. So we're just kind of testing the accelerations in different locations. And there's a lot of information here, but now you have all the components. Again, just evaluated at specific points to try to give you a sense of what's going on with the acceleration field inside the galaxy. These allow you to test disequilibrium. So for example, this is the acceleration in the polar coordinate angle. One is above the plane, one is below the plane. If you're in equilibrium, those should just be mirror images of each other, right? So if they're not the same, but it should be 0 if this is the same as this, just mirrored. And you can see, okay, we are consistent with that equilibrium assumption, even though we didn't bake it in anywhere into our analysis. We get an answer that's at least consistent with it. So that's like a north-south asymmetry. You can also look at asymmetry along the phi direction, kind of sweeping in the plane away from us. And again, we're at least consistent with that assumption of equilibrium. That's mostly a statement about the size of our errors. You could also go back and say, well, I tried to minimize dFdt, like that was the function I was minimizing, but how close did I get to 0, right? Does the data allow me to get to 0? So here I'm showing at the solar location, if you just sample this 10,000 times, you get a whole bunch of measures of dFdt with your best possible guess for the acceleration. Those dFdt's tend not to be 0. So you get kind of a Gaussian smearing around 0. That gives you a sense of how good our technique is right now. The width of this just should tell you, like, the flow is not perfect and how wide is that level of imperfectness. Then we talked to Sukanya Chakrabarty. This is then doing that again, plugging in the quasar measurement for the acceleration. You can see it's a little bit wider, but I don't see any, like, this is not shifted over. If it was shifted over, you're like, disequilibrium, right? Like the true acceleration is not part of what we got from the equilibrium assumption, but this is totally consistent. There's nothing you can withdraw from that. What we're doing right now with Sukanya is she has measurements of accelerations using pulsars and binary systems scattered throughout the galaxy. So now you have a measurement for this acceleration at different locations. And we can ask, are we sensitive to the disequilibrium at those locations? So that's work in progress right now. My guess is that we are going to be statistically consistent with 0 in most locations, but maybe because we know there are these places where the disk is being warped, that we might have some non-trivial disequilibrium that we can see. And certainly I think in the future, there's hope that we will be able to see that disequilibrium.
Yeah, I just got confused because I thought your method still wasn't very accurate in the disk region, or did I miss something?
No, that is another problem that we need to solve. We have thoughts. I think we have a way to solve it, to deal with the dust, but I unfortunately don't have the results to show you right now. But I would say stay tuned, because I think it is something that is solvable. I think we can give an answer in a lot of places where those pulsars are. So then, okay, I went into this because I'm interested in dark matter. So what's the dark matter, right? To take another derivative, we have to do this kernel averaging. We kind of average around a pancake, so that limits our resolution. This is extremely computationally intensive, because you have to just do all these numerical derivatives. What I'm showing here, this is a line through the solar location from kind of the south of the plane through the center to the north. So it's just an arc cutting through where we are. This has the cleanest data because there's very little dust along that line of sight. Each data point here is a statistically independent measure of the second derivative of phi. So it's a measure of the density. You get a continuous function because you can evaluate it anywhere, but what you're doing is averaging over little spheres, so the spheres will overlap. So the fact that this looks sort of like weird and wobbly is because you're seeing, like, you don't have independent measures. All right, this sphere and then the one right next to it are getting some of the same data. So don't look at that, look at the independent data points. You see, oh yeah, you have a disk, that's good. We take them.
What is S? Is that
This is a arc. It's nearly Z, it just curves a little bit.
Okay.
So the point is, all of this should be the same radius from the galactic center, right? That's why we arced it rather than just going straight up and down. And then you subtract off what the best model that we could find for the stars and gas. If you do that, you get a measure of the residual, which is the dark matter, and then you can. If you say these are all at the same R, so if I now impose a symmetry, I could average it, and this is the average value right here. So we have a measure for the dark matter at the solar location. If I
Can
only
we go back to that?
yeah,
Because I didn't understand. Oh, I see. The scale is quite different. Okay. So, oh, I see. Okay. Sorry. I was somehow, yeah, 0 is near the bottom of that residual plot. Okay, good.
yeah, it's
Okay.
statistically off of 0.
Yeah. Cool.
So if you just take the single measurement where we are, we have dark matter, but not at 2 sigma, right? If you then say, okay, put in spherical symmetry and take, all of these like 17 or so independent measures, then you can place a measure on a dark matter component, assuming spherical symmetry, with about a 10% error. This is consistent with previous measurements, so we went through the literature. If you have done this and your paper is not on here, I apologize. But we tried to get a series of recent measurements using various techniques of the density of dark matter in the galaxy, measured where we are. This is our averaged value here, and then these are all of the other ones. We believe that we have competitive and realistic errors, right? We don't have the best measurement, but I think we have propagated our errors through as well as we can. And we don't have, there's certainly inductive bias into the architecture that we put in, but we don't have like a bias based on the model that I assumed of what the shape of the dark matter distribution needed to be. I can then just fit it to an NFW. So instead of going kind of off of the plane, I go in towards the center, right? And so now this is a function of R, we live here, right? And then I get a bunch of measurements of dark matter towards the galactic center and away from the galactic center. You can fit it, it is consistent with an NFW. This is the error on our fit. That would be sort of the standard NFW fit. The error bars are large, right? Because especially as you get towards this end and this end, because you have relatively few stars, it's at the edge of your data.
By the standard, you mean like somebody's fit
Yeah.
to the nocula.
Yeah. And so we're consistent with it, but I would say it's not a terribly interesting measurement yet, but I think it will improve.
Does that fit come from like halo, or from similar radii to this?
So at every radius, we take as many independent, like we did like a nesting problem. How many of our kernel averaging points, could we fit into the sphere that we have data?
Oh, but I mean the one the Euler's one, yeah.
I don't remember enough of what their technique was.
I thought that was stars in the disk.
It's in the disk?
It might be a
Yeah.
rotation curve.
Yeah.
then.
Okay.
I'm
I don't-
not reading the fine print well enough
Yeah,
to
sorry.
know what is you got the solid line and the colored.
Yeah, so these are our data points of like independent measures of the density, which I then say, okay, I'm going to fit all of that scattered data point to this function where I float the central density, RS, and this generalized NFW parameter for the power spectrum. We get an answer that is consistent with what other people have gotten, but I think the plot shows the fit is pretty broad right now.
Not that I have a suggestion as to what you actually should do differently, but is it obvious that like this is the right way to I mean, I understand that these are things you're extracting and then I can fit it to NFW and I can get some information about it.
Yeah.
But is it obvious that like even with your approach that this is the right way that one would want to do
So
this, or that you'd want to sort of like fit directly to?
Yeah, so what we're going to be able to do soon is just give you a function, right? And this has to do this like obnoxious averaging step, right? So in principle, it gives you a function at every point. Eventually, we should just be able to give you a neural network that spits out rho total, and then you subtract off the baryons at any point. And then you could just draw a line, right? And then you probably could try to say, well, is there a greater preference for an NFW versus my favorite model of dark matter? Like, what does it look like there? I would say even with that, you're not going to get a great preference unless your model like turns off all the dark matter in the center, right? The really interesting place where I think a lot of particle physics models change this is, over here, right? I want to get like 1 kiloparsec from the center or closer. Right now, the Gaia data doesn't get me there, right? But if you had another data set or an augmented data set of Gaia plus something else, and you can get closer to the galactic center, and then you can paste this curve maybe to new data. So that's another thing that could be interesting, right? So I don't think right now I'm going to be able to tell you like, oh, the NFW is ruled out, and therefore this other model is better, like cusp versus core or anything like that. Not that you really get that in Milky Way, but that kind of like turnover in the center, that would be way over here, right? It's 0 to 1 kiloparsec. So this is sort of like baby steps, but I think it's generalizable if you can get a clean data set closer to the galactic center. And there are, I think, some maybe combinations of data that could get us that, not from a single measurement, but from combinations.
Could you say a bit about how you subtract baryons?
So this is, there it is. This model here is the model we're using. Sorry, I have it written down somewhere on one of the slides of which exact model we're using. It is a analytic model that is fit to a huge number of data sets, so a bunch of different stellar populations and gas populations, and you add them together. We are at least trying to include that error there, right? And here, that is a significant component of the error budget for this data point. That's a lot of the error here is coming just from the spread in that functional form, right? I'm in no way an expert on how that model was constructed, so I kind of just have to take it, as read that they, did their modeling more or less correctly. But what you see is out here, it doesn't matter, right? We are far enough off of the disk that how much, the baryonic component is completely irrelevant, because it's just completely so dominant by every model of it. So you have to be very, very wrong out here for the baryons to add up, because that's far off the disk. Right? One of the goals going into this project was to get more than 2 kiloparsecs off of the disk, right? Because once you're over there, there's just really no baryons to speak of.
Is that based on
Yeah, it's based on observations of stars and gas.
If that's the case, it should be that, right, as you go for larger S than negative or positive, right, the asymptotic value for your data point should be the dark matter density,
Yes.
basically. But it looks, I mean, maybe it's a little bit hard to tell, but I mean,
It's
by eye, it
specificity.
looks like it falls off so a little bit.
Yeah, I think if we hadn't drawn the gray, I think you would just see, oh, the errors are getting bigger.
Sure, sure.
Yeah. So I think there's a lot of improvements coming down the pipe. In one case, just data, DR4 and DR5, we're gonna have 5 times the data set, so that by itself will just improve everything. And the errors will get much smaller. We have a technique to get rid of the most computationally expensive part of our calculation and replace it with a much more lightweight calculation. We can speed this up, you can get a continuous function for the output of your density. It also requires it to actually be the gradient. The accelerations are now a gradient of a function, which you probably want. So this is a technical point. If you're paying attention to machine learning, we occasionally get people who are like, oh, maths, normalizing flows, those are old, right? Like it's like the singularity, right? You turn around and somebody's like, Facebook has a new algorithm out there. So the new hotness is flow matching. We tested with that very extensively, and it turns out in this context, not every context, the maths do better. So we have looked at new architectures, but we're sticking with the one we have. And a full 3D map of the sphere around us is kind of on its way. Figuring out how to make that visible on the paper is going to be a fun experiment. But we also have, I think, ways to approach the dust and to talk to people who are measuring accelerations and get measures of the distant quarter. So I will say, whenever I write this talk, I just kind of throw in a bunch of things that I'm doing on these data sets with machine learning. I think by far this is the most, kind of cutting edge and, data intensive and gives you a really interesting result. So I spend a lot of time on it. I can flip through a couple of the other things I can talk about, but, given that I just spent 50 minutes on this, I'm not going to go through the others in nearly as much detail. I'll just say one other thing you can do is look in the data for overdensities, for anomalies. Within the Gaia data, there should be weird collections of stars that don't look like the stars around them. Like, for example, stellar streams, lines of stars all moving together. That should be an overdensity in this phase space. This is actually kind of one of the first places we started with machine learning. My colleague, David Shee at Rutgers, had been thinking about finding weird data at the LHC for a really long time. So he was looking at what's called anomaly detection. And they developed a tool called Anode. And what Anode uses is the fact that if you had, let's say you have, like, this is the LHC, you have 2 parameters you're measuring, you have a suspicion that one of those parameters should have an anomaly, like that can be localized. So you have a search region here and you want to find this little clump of red dots, right? You then have sidebands, and you can interpolate the phase space density from the sideband into your search region. And the most general anomaly score you can build is the phase space density in the region you're trying to look for divided by the phase space density outside the region you want to look at. This ratio should be greater than 1 near those weird data points. So that's something they've applied in LHC, and the advantage here is that you have normalizing flows. You can learn these functions without knowing anything about it. Right? You don't need to know what these are. They just, the machine learning gives you that. You can then throw this problem at Gaia, which is really fun because the data is very different from the LHC. But this is just a toy example using this stream GD1. Those are the stream stars in red as identified by Price, Williams, and Manaka. Blue is all of the Gaia stars in this sample, right? So that's in position, that's in proper motion, that's in color and magnitude. This R is our anomaly score. You notice all of the stars have this broad distribution, but these unusual stream stars tend to have large anomaly scores. So if you cut on that, this stream pops right out, right? Because they're the anomalous ones. They're the weird looking ones. I'll skip through. We then ran it on the full sky, and then using what we call via Machina 1, you just recover this GD1. We then spent a huge amount of time improving the algorithm, and now you can recover the stream in pretty high accuracy using just this anomaly score without knowing any, where this stream is. You just feed it into your algorithm and it kicks out. Here, these stars do not look like the ones near them, is basically what it's saying.
I was wondering how many stars are in these strings, like in each string?
Okay, so the hidden, the dirty secret here is I'm showing you GD1, which as everyone at CCA will tell me, anyone can find this stream. This one has, it's over 1,000 stars, right?
It's retrograde, which makes it
Yeah, and
easier.
if you look at the data long enough, and if you have astronomer eyes, which I don't have, but one of the fun things about doing machine learning on Astro data is you discover that there are really good neural nets and they're called astronomers, right? You just like show them the data, they're like, well, that's weird. You're like, I have no idea what you're looking at. So like astronomers can pick this out as long as you like put the data in the right form. So the fact that we can, with great expense, get a neural network to do it is not terribly interesting. Let me show you the next slide before you're like, why is he talking about that? Sorry, you had a
I was
question.
just gonna ask, but you might get to that now when you said you would spend time improving and then you picked out GD1 even better. Would that apply to any other stream or was this like optimized to GD1?
It wasn't optimized only to GD1. It was optimized for other streams in this, other known streams.
Yeah.
Because then what we can do is just run this over the entire sky. One sec. Run it over the entire sky and then cut out all the streams that people already know. Right, and so this is the sky, you know, galactic L, so along the plane, off of the plane. The black ones are known streams. The colored are the top 15 stream candidates as identified by this algorithm. Right, so I have no idea if those are streams or not. You can. The other nice thing about doing Astro data, unlike the LHC I just have to wait. Right, and eventually they'll give me more data, and that will tell me that that bump went away. Right. There are other ways to look, like Gaia looks at a lot of stars, but doesn't look, you know, it doesn't give you all the information about a star. So, you know, we are talking to other astronomers to like, go back and look in those other surveys. And if there isn't something there, you can have a telescope look at it and tell you whether these stars really look similar and have properties that were expected of a stellar stream, not just, hey, they make a line in your data. There was a question back there, yeah.
Sorry, I was just wondering also, like, what's the source of the stellar streams? Are they meant to be?
Yeah, sorry, I skipped through that. What they are, these are probably mostly globular clusters. So they were born in kind of a blob of stars and they're being tidally stripped by the gravitational potential. What I would like them, the reason I'm interested in this as a particle physicist is that for one thing, they are tracers of the potential. Once you have a huge population of streams, you can ask what potential underlying them would give you a set of orbits that's consistent. Right, for every single one of these streams should be evolving in the same potential. So you could try to back that out. The other thing is that there might be a dwarf galaxy in one of these. The other population that could give you these things could be a dwarf galaxy that's getting tidally stripped.
Yeah, I was just curious, so I think there are about like 70 known globular cluster streams in the Milky Way, but did you recover all of those?
We do not recover all of the streams. So these have to be within the Gaia data with non-zero proper motion, which cuts out many of the streams that are known.
Yeah.
And then we have done simulation and we tried to figure out where our sensitivity is. There is a minimum number of stars that we're just not sensitive to. It's like it's a density, it's just number of stars per angle, basically. And a lot of them are just 2gen. And there are some that we believe we should have gotten that we didn't, right? We get many of the ones we think we should got, but every now and then we're like, we don't know why you did not see this. We are doing an improvement, and the LHC people have taken anode, and of course now we have cathode. That just improves your anomaly score, and so that should really help. There's another thing with Ben Nachman and company. So there's another anomaly detector called Koala. So now it's Koala in space. Koala does not seem to be as good at getting the anomaly score, but it's much, much faster. It takes a lot less computation, and so that has advantages, right? Like doing the entire sky with our technique is really, really expensive. So there might be something nice to be able to say, I can run this quickly, it's not as good, but you know that allows me to ask a lot more questions. The last thing is that we can generate nice synthetic galaxies. I'm going to skip all this. If you happen to be in the market for a synthetic galaxy, a set of observations for Gaia or something like that, we are in the process of being able to do that. And these are plots that were sent to me last week by the grad student who's working on it, taking an n-body simulation of galaxies and turning that into a very consistent set of simulated stars. The machine learning lets you do this much faster and with greater smoothing than the traditional techniques. The reason we discovered this actually is that this is the traditional technique. You take a simulation of stars and then you generate fake stars on top of that. Notice all of the blobs, right? Every one of those is a star particle, which then gets turned into 1,000 stars or 10,000 stars. We ran our anomaly detector on this and it worked really well. That's anomalous and that's anomalous and that's anomalous. It just yelled at us. It's like every single star here is weird. And so we needed to find a new way to do it, and we think we have found it using these normalizing stars. So I rushed through two other things at the end. If you're interested in those, please come by and talk to me. What I wanted to kind of just give you a sense of, so there's a lot of hype about machine learning. I think people should be rightfully skeptical of it. If the data doesn't contain the information you want, no machine is going to give you what you need. There are sort of, I think, reasonable ways to take these tools, apply our physics and astrophysics intuition and knowledge, like this actually use like the Boltzmann equation, right? There is a physical equation and the machine is just giving you a useful tool as an intermediate step. But it really allows you to look at very large data sets in interesting and new ways that are really difficult to do otherwise. So we can do anomaly searching. I've done it for stellar streams here, but you could apply it to other things. We can create fake galaxies faster, better, and hopefully cheaper than existing ways. Not sure about the cheaper, maybe. And then you can kind of use real data to measure the galactic potential underneath. So these are a lot of things I've been kind of working on. I hope one day to be able to take all of this and go back to where I started and say, what models of dark matter really give me those answers? It might be that we're just not sensitive enough to that yet. But I think this data contains a lot of information that hasn't been fully exploited. But it's really exciting to kind of get in there, see what it can tell us, and then see, hopefully, what theories are consistent with that. So with that, thank you. And again, the slides that I skipped through, you're like, wait a minute, that sounded important. Talk to me afterwards or ask a question.
Any questions from that? I have one. I think you said at the beginning or earlier in your talk that you really wish you had data near the galactic center because you can test more of these dark matter models.
Yeah.
You said there were some prospects.
There are, we have talked to a couple of people who say that they have, if you combine a bunch of surveys, you might have stars near the galactic center. The problem is they're not like, it's an ugly footprint, right? So it's like a wedge of stars where the galactic center is here, just a wedge sticking off the side, right? In principle, that set of stars should internally, obey the Boltzmann equation, even though you don't have all of the stars outside of it, right? But then you have to worry about, do you have full completeness, right? Like, because if there's stars in there that you should have seen, should be part of your data and aren't, right? Well, the network doesn't know that, right? So it will just fit the density of the data, not the density of the stars that the data trace. And we're trying to figure that out. It's early days. I'm worried that we're going to have a lot of problems. So I think, I'm not promising a result anytime soon, but there is more data out there that can be combined and looked at in interesting ways. And I think these techniques could help you in that, but it's going to be a lot of work to do this. The other thing I'll say for a lot of machine learning, I think the advantage you get is you end up staring at the data for so long yourself that you get really familiar with it and start learning all the tricks and problems with it. And then the machine tells you something else, right?
Regarding that, do you need proper motions? Like, can you do things with radial velocities?
You could, but then you'd have to put in a symmetry assumption. Okay. Right. I mean, there might be clever,
like isotropic or beta or something.
Yeah, that would be the most obvious thing to do. There might be ways, and people, I think Mary Angela's group had a paper a couple of years ago where they tried to infill data. Like, you have a set of data that has 60, and you have a set of data that only has 5. You're missing like one of the components. Can you guess what that missing component should be given the other? That's certainly a thing you can do. I think you should be rightfully skeptical, right? Because the star that doesn't have that data could be coming from a different population from the star that does, right? So, you could do that and then you could run all this through, but are you robust to those errors? I mean, that's one of the reasons that we are trying to do these upsampling projects, is we really would like to be able to totally control this problem and know what the answer is and run through and sort of like, it's the Milky Way, except I know the answer. And the simulations right now, like, we just run into a separate problem, which is we don't have enough stars, right? So we want to be able to answer that, and for our purposes, and I think other people might find it useful, so we'll try to make it as a tool that you take your simulation, run it through, and get a synthetic observation. Sorry.
Well, if other have, listen, I wanted to get a better feel for what it's like using a normalizing flow. And sort of how much, I mean, what if you had stuck a lot of other information in, like metallicity and age and stuff?
Yeah, you
Would
can
it
just
have
do that.
Somehow,
Yeah, and in fact,
just sort of, but also, this Mathematica probably doesn't have them in it. Or maybe it does. I
so
don't
there
know.
are Python packages, and like these days, basically what I do is I ask my postdocs. So Sung-Hak Lim, who has been the first author on a bunch of these papers, is amazing, right? Like he understands the physics, and he's also really good at getting these things to work. And then they, I say, hey, can you send me that network so I could play around with it? But you can't, like, once you've seen, if you have some Python skills, like, can read it, there are networks out there you can just download and put in. The problem is that to get it to work with this data, sometimes you need to do a bunch of pre-processing. Normalizing flows hate edges, because you're learning, if you're mapping a Gaussian to your data. If your data goes like that, the Gaussian is going to hate it, right? Because you get ringing in the edges. But you can learn tricks to remove that as much as you can. This one actually, going to the metallicity and stuff like that, these are conditional flows. So you're learning the phase space density in X and V conditioned on metallicity, conditioned on age, because it's a simulation, so I have those values. So 6 dimensions is like a large number of dimensions to like do binning, like a genes analysis. It's a very small dimension for normalizing flow. These things are supposed to be like applied to 100-dimensional data, right? So it's not a problem in that aspect. And it's been really nice because there was a team of people doing LHC data that you had somebody you can ask. But it really started because we had one grad student who wanted to do this, trained a bunch of networks, and then can show you how to do it, and then you just kind of go from there.
What are your thoughts on removing the dust? Like, how do you think about doing that?
Ask me when I'm not being recorded. But yeah, it's